Welcome back. So far we have covered rotational kinematics. Today we're going to start going over rotational dynamics. So when we covered translational dynamics in chapter 4, we discovered that a net force was necessary to cause an object to accelerate. In rotational dynamics, we're going to discover what causes an object to rotationally accelerate, or what causes angular acceleration. So in translational dynamics, we found that a translational acceleration is produced by a net force. This is simply Newton's second law. In rotational dynamics, the acceleration is angular, which is related to the translational acceleration by this formula. We can simply sub in our tangential acceleration into the second law, and we'll end up with a net force equals mass times radius times the angular acceleration. However, angular acceleration cannot be produced by translational forces alone. There must be some lever arm. So what we're going to do is create a lever arm. We're going to create an R, but what we do on one side of the equation we have to do to the other side of the equation. So we're going to multiply both sides of our equation times R. And you'll see what we have here is a torque. A force times the lever arm is a torque, equals mr squared times the angular acceleration. So if we look at Newton's second law, the force equals mass times acceleration. The net force is on one side of the equation. On the other side of the equation, we have mass times translational acceleration. The mass is translational inertia. The equivalent to that in rotational dynamics is our torque equals our rotational inertia times the angular acceleration. Now our rotational inertia is going to be different depending on the object that is rotating. You'll probably notice that it is easier to rotate a tire down a road than it is to rotate a giant massive square block. They have different rotational inertias. In fact, you ought to get a little bit familiar with this table. You'll find it in your book, and you may ask yourself, how do I use this? Well, first you'll have to look at the problem and say, what is this object that I'm being asked to work best modeled by? If you have a tire, it could be D, a hollow cylinder, or it could also be C, a solid cylinder. It depends on what's in your problem. If it gives you an inner and outer radius for your tire, it's going to be a hollow cylinder. If not, it'll probably just be a solid cylinder. And then you're going to ask, about what axis is the object rotating? Are you turning a tire on a car axle, such as in A? Or are you turning the tire by flipping it end over end like you would flip a coin, such as B? Finally, what you're going to end up with when you decide what object and what rotation you're using, you're going to end up with moment of inertia. And this moment of inertia can be substituted in for the I of our equation. So how do you do rotational dynamic problems? First, you get very clear on your problem. You draw a picture, draw it in your head, draw it on the paper. Draw the forces that are acting on it and around what axis the forces are going. Once you're very clear on what's going on in the problem, look at what you need to know and pick an appropriate equation. Then you want to make your life a little bit easier and get rid of things that you don't need. Use the zeros of your equation to get rid of things you don't need. Then you'll want to algebraically solve the equation you have left for what you want, and then plug some numbers in and go to town. So let's go ahead and do a couple of problems. In the first problem, we've got a wheel on a wagon with a uniform radius of 50 centimeters. It's jacked up off of the ground and is rotating at a constant angular speed of 25 radians per second when the driver applies the brake. If the brake provides a frictional force of 12 newtons and the wagon wheel comes to a stop after 6 seconds, what is the moment of inertia of the wheel? So drawing a quick picture here, we have our wheel. It is rotating clockwise, so we'll note that it is a negative velocity. And the force, we look at this wheel, it looks like it's going to be pretty darn perpendicular to our axis. Theta equals 90 degrees. So we're going to solve this. So we know that the sum of our torques is going to equal the radius times the force that is perpendicular to our radius. In this case, we've got a sine of 90. That sine ends up going away. Now, the sum of our torques is also equal to the moment of inertia times the radial acceleration. Now in this problem, remember, we're looking for the moment of inertia of this wheel. So we'll go ahead and solve for that. And we're left on the bottom of our equation with a rotational acceleration. How are we going to find that? We're going to find that by converting the angular speed that we have and the time that we have into an acceleration. So the change of our speed divided by the time is going to be our angular acceleration. If we go ahead and plug this all into our equation that we found up here, we're going to find a half meter times 12 newtons times 1 divided by the 4.17 radians per second square is going to equal 1.44 newton meters per second squared. We can solve those units down a little bit to get a 1.44 kilograms meter squared. So our next problem is another wheel. We've got a 15 newton force applied to a cord wrapped around a pulley with a mass of about 4 kilos and radius of 33 centimeters. If there's a frictional torque of 1.1 newton meters at the axle, what is the angular acceleration of the pulley? And we can go ahead and approximate the pulley as a solid cylinder which has a rotational inertia of 1/2 mr squared. So one quick thing I want to show you is we can turn these rotational problems into linear problems if we really want to, if that visually helps you a bit. If you look at this problem, this is a perpendicular force. We can just stretch this out right here. This frictional force doesn't necessarily have to point in this direction. We know the frictional force is going to be a clockwise force. We can just think of this as a long lever arm with our pivot point right here in the center, with this being R and this being R. So the problem, the sum of the torques is going to be R times the force of tension, that's a positive number, it's going in the counterclockwise direction, minus the torque of the friction, and that has to equal to I times alpha. If we go ahead and plug in our I, which we know is 1/2 mr squared, and solve for alpha, we get this equation. And then all we're going to do is plug in a little numbers and go to town with a 17.68 radians per second acceleration. So as always, thank you for watching this video, and please check As You Learn for any additional assignments.